When I introduced recurrent neural networks, I made it sound like they were going to have impressive performance, we were going to be able to classify movie reviews better than ever before by their sentiment. And then the recurrent neural network that we just built, it performed pretty terribly, didn't it? It's actually the worst performance we've had yet. So the reason why we used a simple RNN was to kind of iteratively build our knowledge. So we used an RNN, and in practice, RNNs are used seldom in natural language processing, at least in their simple vanilla form with just that single tanh layer inside of each of the little neural networks. So recall from the diagram earlier, when I was explaining recurrent neural networks, we had a sentence, deep learning for natural language processing, and each of those words, each of those tokens, was passed into an individual little neural network module. What I've done here is I've made this quite a bit larger. Earlier we didn't need to with just the simple RNN because we only had a tanh layer inside. It didn't seem like it was worth getting into too much detail. But what we want to be doing now is building upon that simple RNN unit for a long, short-term memory cell. So the problem with the simple RNNs was that they just backpropagate through time. They just backpropagate over the previous words in the sentence. And they aren't able to assign too much weight, to vary their weight too much based on the importance of that information going back. And they can't stretch very far back through time. So after about 10 time steps, the vanishing gradient problem means that we're rarely able to get information from 11 words before the current word learning. And sometimes those words are quite important to figuring out our downstream task like sentiment classification in our network. So the trick that long short-term memory units have, they have quite a bit more complexity going on within the neural network module. So in addition to the tanh layer that the simple RNN had, the LSTM variant also has 3 sigmoid gates inside of it. So recall that sigmoid neurons have output values from 0 to 1. In this instance, that enables them to act as gates for information. So they can decide how much information to pass through. Clearly, if they weight down to 0, then no information is being passed through. If they weight up to 1, then all that information is being passed through. And so these 3 gates, the forget gate, the input gate, and the output gate, they enable information about words in the past to be retained if they appear to be important for the task later on, like sentiment classification. So this means, for example, if gender is important to predicting the next word in the sequence, and a gender indicating word like he or she happened quite a bit earlier in the sentence, this complex structure of a gating structure enables that critical piece of information, the use of he or she, maybe 20 or 30 or 40 words earlier in the sentence, to impact the later parts of the sentence, the current part of the sentence. So to go into detail here on this right now in these live lessons, it would take far too long. I highly recommend checking out Chris Ola's blog, O-L-A-H. He has a blog post called Understanding LSTMs, and it will go into all of the detail of how the information from a given word interacts with hidden state information and cell state information from previous time steps, is then has operations performed on all of that information inside of the module, involving these gates and the TNH layer, and then any given module outputs that hidden state information both to the next cell as well as to the next layer, and it also passes along the cell state information. So all in all, this is far too complex a theory to go into a huge amount of detail here, but we know that the theory is sound from the way that these networks work really well. So we'll, in next step in these live lessons, we will drop out our RNN layer from our network and we'll replace it with an LSTM layer, and you'll see the impact on performance. There's another variant on the RNN that is talked about a lot in the literature today, and that's the gated recurrent unit, or the GRU. Gated recurrent units are quite similar in idea to the LSTM, so they're also designed to selectively retain information from the past using this gate idea within modules. The GRUs only have 2 gates instead of 3. And there are some other more nuanced differences between the two. The GRU was invented later, about 15 years later than the LSTM. It was a 2014 paper by Cho and colleagues that brought this idea to the fore. And the GRUs, in some instances, work more efficiently than LSTMs. In practice, I have found that LSTMs tend to work better if the LSTM doesn't need to make use of its extra third gate, then it doesn't. So kind of all of the functionality of our GRU is captured in an LSTM plus a little bit more. So I tend to use LSTMs, but up next, I'll show you how to use GRUs as well in case you're interested in trying those out in your network. Let's get to it.